This video deals with coordinates, time-like world lines, basis vectors, geodesics, and motion in flat and curved spacetimes. It then looks at symmetries of spacetime metrics and how they can be used to identify conserved quantities such as energy and momentum. So let's consider the movement of particles or objects in spacetime that have a finite mass. And we can represent that on a spacetime diagram. Its world line is the dotted red line here. The tangent vector is its forward velocity. We have two spatial and one time dimension shown here. And the coordinates here, we can express this path in terms of the proper time carried by, that's the proper time of the object is, the object carries a clock with it and measures its own time, so we can parameterize the path using that, even though here we've used coordinate time. And the relationship between proper time and coordinate time will come up shortly, but mostly I'm interested throughout this video in dealing with these coordinates here as a function of the proper time of the particle, and then its forward velocity is then the derivative with respect to the proper time of each of these coordinates. And so that's how we get the forward velocity vector. Even though here the space-time diagram involves a coordinate time t, but shortly we'll see there's a relationship. All right, so a universal coordinate system can be used in flat space-time only, but not in curved space-time. In flat space-time, the basis vectors are the same everywhere, and so it's possible to use a single coordinate system to cover the whole of space-time. All right, now in curved space-time, a coordinate system is local to the point where it's defined and applies to a small region around it. We can't cover the entire curved space with a single coordinate system. The basis vectors are not constant everywhere. They depend on position and they change. They may not even be of unit length or even orthogonal to each other. Okay, so again here I've used a two-dimensional space-time diagram here with coordinate time t and position x, but we're going to be very shortly interested in the path of a particle parameterized in terms of its proper time. And that's the time it measures as it carries a clock with itself, so to speak, and records its own time. Okay, now the metric of curved space-time is composed of basis vectors that depend on position and do not need to be unit length or even orthogonal. These vectors are collectively called the coordinate basis. All right. Now let's just have a look. The forward velocity in terms of the derivative of the coordinates with respect to proper time, and we find that that's related to coordinate time. dx0, x0 was the coordinate ct, and c dt d tau gives us the first component of the forward velocity, the time component of the forward velocity. The first spatial component, dx1 dt, coordinate time t, times dt d tau, tau the proper time. Okay, that's how they're related. This dt d tau is of course the gamma factor. Okay, so the forward velocity can be written as c times gamma, and then gamma times each of the derivatives of the spatial coordinates with respect to coordinate time. Okay, so we can represent it like this. The magnitude of the forward velocity for a particle with mass is this object here. I've explained this in a separate video elsewhere. I don't intend to go to that again. I'm simply, with these first couple of slides, setting the stage for what I want to look at. But anyway, for a particle with mass, the magnitude of the forward velocity comes out to be this constant minus c squared. In the case of a particle with zero mass, a massless particle, then this here is equal to 0. But I'm not so concerned about that today. But anyway, just to remind you, the coordinates of the particle of its world line, the world line traced out by the particle can be expressed in its coordinates x0 of tau, x1 of tau, x2 of tau, x3 of tau, and remembering that there's a relationship between the coordinate time t and the proper time tau, and that's this factor of gamma, the gamma from special relativity. If we just have a look here, this supplies us with an interesting following relationship. If we separate the differentials a bit, and we have the line element squared is g mu nu dx nu, but if we multiply through by d tau squared, so that we have minus c squared times d tau squared, we have that the line element for a time-like world line is less than 0, at least for the metric that I'm using in these videos. I'm using the metric that has the time element, or the 0, 0 component, being negative and the spatial ones being positive. Okay, so now let's come now to freely falling particles. So freely falling particles with finite mass travel along time-like world lines, meaning ds squared is 0. Massless particles travel along null world lines, so ds squared is 0. All right, so world line here, and again, we're using coordinates. But at each point P, we can establish a local coordinate system composed of 4 orthogonal unit vectors. Now, 3 of those are shown here. We have the time-like basis vector, and it is not orthonormal basis vector because it is here, you can see with the hat here indicating it's orthonormal, so it's of unit length and orthogonal to all the others. The first 2 spatial ones, spatial basis vectors, orthonormal ones, E2, E3 is obviously suppressed, and the time-like basis vector E0 hat is tangent to the world line of the particle. So we can take it as being tangent to the world line of the particle. We'll come back a little bit more to that. All right, now, in this local coordinate system, observations are made by observers both at rest in an inertial frame and with respect to the axes of that frame. So we can have a freely falling particle, or we could have a freely falling laboratory. And in that laboratory is an observer, and an observer establishes, according to the laboratory, a system of orthonormal basis vectors for the spatial axes, and then can use the clock as their time axis. So an observer in space-time can be thought of as contained within a small laboratory that moves along a time-like world line, ds squared less than 0, and observations are made with respect to the axes and the clock of this laboratory. So our clock is ticking away 1 second at a time at a constant rate, and so the basis vector in the time direction can be an orthonormal basis vector of unit length, each unit a second, and pointing in the direction of increasing time. And that was the E0 basis vector we saw on the previous slide. So a freely falling particle, a test particle, 1 kilogram mass, or some other particle of any other mass, or a laboratory and observer in it, all of these can be freely falling in space-time, meaning that there's no forces acting on them and they are free to follow the curvature of space-time. All right. Now, the clock at rest in this laboratory defines a time direction that is related to the forward velocity of the observer, forward velocity vector of the observer, sorry. So the forward velocity of an observer in the laboratory is, if I just normalize it here, 1 on C, U observer. Okay, now the spatial part here, the observer is not moving with respect to the laboratory, so the spatial part here goes to 0. We're just left with a time component. Okay, gamma is 1 because the observer is not moving with respect to the laboratory. And so we take gamma as 1. And what we end up with is our basis vector we saw in the previous diagram right here, this one here. And each of these is unit, so it's of unit length, each unit 1 second or 1 unit of time, what have you, pointing in the increasing direction, time direction. If the laboratory is at rest in some other inertial frame, then its axes will align with those of the inertial frame itself. So assuming it's not rotated or anything, but it can align with those. But the observer can make the axes of the laboratory, the walls, if you like, as we saw on the previous slide, can make that their basis against which they make measurements. Okay, now the world lines followed by free particles between points that are separated by time-like intervals extremizes the proper time tau. So we've got a world line here. Again, I'm using coordinate time, not proper time. And this interval here from E1, some event here, to some event here, okay, these extremal proper time world lines are called geodesics. Okay, and that's what we're coming at. We're going to look at how we arrive at those. In flat Euclidean space and Minkowski space-time, these geodesics are straight lines. Okay, but that's not the case in curved space. And we're just coming back to what we saw earlier. Remember, the line element squared was minus c squared d tau squared was equal to this object. So we just multiply through by -1 here. Let's have a look at this. Square root both sides. We've got c d tau is this object here, which we're going to use very shortly. So world lines of free particles between points that are separated by time-like intervals, extremized as a proper time. All that's happening is a free particle travels along geodesics. So a free particle, no forces acting on it, it's following the curvature of space-time, it will travel along geodesics. All right, and we're going to have a look at how we identify those geodesics. And we can do that by extremizing the proper time, which is why we're going to be using these relationships down here, particularly this final one. Okay, so the proper time tau along the geodesic between two events shown below, between E1 and E2 there, is going to be the integral E1 to E2 d tau, or the integral of that relationship we found on the last slide there. So it's 1 on c times the square root of this object here. Okay, we can carry out that integral if we just parameterize the path in terms of some variable lambda. So we're going to parameterize the world line in terms of some parameter lambda. So x of mu will be x mu of lambda. It could be the proper time that we use. It could be, for the purpose of integration up here, it'll be more convenient to use another parameter. And this parameter lambda will go from 0 to 1. Okay, lambda is 0 here, lambda is 1 here. And the total proper time taken between the two events is then the integral 0 to 1, 1 on c, square of this object here. See how dx mu d lambda, dx nu d lambda, and then integrate with respect to lambda. All right, so we're now ready to find time-like geodesics for a given space-time by finding the extremum of some Lagrangian. So the condition for extremizing the proper time is, and because this is what gives us, by extremizing the proper time, we locate the geodesics. So delta is the variation of the integral d tau. We can take the delta, the variation symbol inside the integral, d tau here is equal to 0. Now this proper time interval can be expressed in terms of a Lagrangian. The Lagrangian, remember, is a function of the coordinates and then the derivative of the coordinates. Okay, and again we have, if we choose our Lagrangian, this object here, this, if you look at it, dx mu d lambda is the derivative of the coordinates, if you like, the speed. And so here, this would give us the square root of the magnitude of the speed, and it would be, if you can imagine, the speed per unit of mass. Okay, so Lagrangian takes that form because if you think of Lagrangian in terms of the kinetic energy minus potential, a free particle has no potential. So there's none of that here. There's no dependence on position. We're just interested in here, which is really equivalent to sort of speed, because these are the tangent vectors here to the world line, which is the forward velocity of the particle. The magnitude of that is the speed. All right, so we have the integral, the proper time, the total proper time between event 1 and event 2, with the integral of the Lagrangian with respect to d lambda, integrated with respect to lambda. And really, I've just repeated myself there again. All right. Okay. Now treat this as a variational problem. So the integral of the delta variation in d tau is the integral from 0 to 1, the variation Lagrangian d lambda equals 0. Now just note there's a couple of things here that help us. D tau is L times d lambda. And just rearranging that d lambda, d tau is 1 on L. We'll make use of that shortly. Okay, so perform this, which is not the focus of this video, but if you do perform this calculation, you'll end up with the Euler-Langrange equation. If you perform the variation, you'll end up with the Euler-Langrange equation, which takes this form here. And we can use this now. This will give us the geodesics. Now we know, for instance, example in Minkowski space, these geodesics take the form of straight lines. So let's just have a look here, x mu. Let's look at the x1 direction, the x1 coordinate. Our metric in flat Minkowski space is eta mu nu, which is -1. The signature I'm using always on this channel is -1 in the time component, and the 3 spatial ones along the diagonal are +1. L is this object here, substituting in. We have the x1 coordinate, and then mu is left free to vary. dl dx1 from our Lagrangian, if you remember on the previous slide, is 0. Remember, here's Lagrangian here. There's no dependence on the x1 coordinate, only on the derivatives of each of the coordinates. So this bit is 0, so that bit disappears. We're only left concerned with this part in here. Let's have a look at that. Okay, which means we have minus d lambda, this partial derivative of Lagrangian with respect to the derivative of the coordinate. Expanding that out, we have this. Okay, so the partial derivative of the Lagrangian with respect to this term here is this object here times that. Okay, remember, square root, take it downstairs, 1 on 2 times the square root of that times the object inside. All right. Okay, now, next bit. And when we differentiate with respect to dx mu d lambda, we caused, that should be actually a 1 there. We actually differentiate, we got rid of that, and we're left with this negative eta 1 nu dx nu d lambda, that goes there. Okay, now when that happens here, the only term of this metric here that counts is nu must be 1. Okay, otherwise it's 0 for all others, and so we're left with dx1 d lambda here. We get 1/2 times d lambda 1 and L dx1 d lambda, and we understand that to be 0. That's the point of the Lagrangian equations. That's set to 0. Now that leads to, if we work with that, is 1/2 times d lambda d tau times d lambda. So we're going to multiply through by d lambda d tau, which we saw on the previous page. That gave us a certain relation, times d lambda, that one there. Okay, now dx1 L d lambda is this bit here. Well, we saw that before that L d lambda on the previous slide was equal to d tau. So we have 1/2 d tau, dx1 d tau, and when we work through that, we have 1/2 d2 x1 d tau squared equals 0, indicating, so doing this for each of the coordinates gives us this, which tells us that geodesics in Minkowski space are straight lines. The acceleration is equal to 0. It's the movement of a free particle. No forces acting on it. They move in straight lines because no forces are acting. And so geodesics in Minkowski space are straight lines. All right, notice how the metric is involved in finding the geodesics in a given space-time. The metric tells us about the geometry of a space-time or manifold, including any underlying symmetries or isometries. Now, symmetry arises when a metric is independent of a coordinate, so the transformation or change in that coordinate leaves the metric invariant. And by that I mean that, so for example, for a space-time coordinate x0 that is absent from the metric, then the transformation x0 to x0 plus a constant will leave the metric unchanged because it doesn't appear in the metric. All right, so any transformation, adding on a constant, moving in that particular direction doesn't change the metric because it's independent of that coordinate. Now, thanks to Noether's theorem, we know that a space-time symmetry implies a conserved quantity. So for each symmetry, we can define a unit vector called a killing vector. Okay, for each of these symmetries or isometries, we can define a killing vector field. And okay, so for some metric g mu nu that is independent of the x0 coordinate, we have this object here, reminding ourselves of the Lagrangian equation here. X mu is x0, g mu nu, L is this object here. Okay, dl dx0 is 0. All right, the only dependence in this Lagrangian is on the derivatives of the coordinates, not on the individual coordinates itself. All right, so that means that that bit there drops off. Okay, and we're left with just this first part. Here we are there. Now let's substitute in d lambda. Now the x mu here, I could put 0, I probably should have, but we have minus d lambda 1 on 2L times this object here. Okay, is d lambda 1/2 g 0 nu 1 on L dx mu d lambda. Okay, and I just brought the L from over here because there's a reason for that. We'll see next line down is d lambda half g 0 nu dx nu d tau. Remember L times d lambda was d tau. All right. And just remember this part just comes from differentiating this bit here. Instead of including a big square root sign down here and taking up a few lines on the slide, I can simply write that you've taken the power of plus a half here. It's become negative a half, so you've got 1 over the square root of that. So you've just got 1 over L. Okay. Now all that's set to 0. And let's go on a little bit further. So we have 2 multiplying through by d lambda d tau, because remember it equals 0, so we can multiply both sides by d lambda d tau. Okay, cancels out the lambda here. We're left with d tau, and we have I can multiply through the 2 by a half, disappears, and we're left with just this object here. Now the bit, obviously here the only value nu can be for a diagonal metric, if that's what we're working with, would be 0, and I could go straight to 0 here, but I'll just stop for a moment and pause, because the bit inside the bracket looks, well, a bit like the scalar product of 2 vectors. Because remember in curved space, when you want to take the scalar product with 2 vectors to find the magnitude, you've got 2 upper indices, and then you've got the metric here with these 2 lower indices, and that lowers one of the indices so that you can take the scalar product and result in the contraction of the 2 vectors to give you a scalar, because you have to have 1 up and 1 down according to the summation convention. But that sort of looks like we're missing a vector in here. Looks like we're missing something in order to carry out this contraction. So the bit inside the brackets looks like the scalar product of 2 vectors, which we're allowed to do if we use a second vector that is a constant. So we can stick a constant in here, because that doesn't affect the end result of this being equal to 0, because the derivative here will still give us 0. All right. So for our metric, let it be independent of the x0 coordinate, and so a suitable killing vector is k mu is 1, 0, 0, 0. So a 1 in the 0 component area. That gives us a constant vector. There's no variable there. So let's come back here and stick that in here. Sticking a 1 in doesn't change anything. G0 nu becomes G mu nu K mu. Okay. And doesn't change anything, because really that mu is a 0 there. So there's a 0 there, so I haven't changed anything. Dx nu d tau is d tau G mu nu K mu U nu. All right. Which is really, if we can, it's really this metric here lowers this mu, if you like, makes it mu, and then you can contract and produce the scalar. And that's really the scalar product of the vector k with the vector u. All right. And the derivative of that is 0. Well, that tells us that k dot u is constant. Okay, u is the fall velocity of the object, k is the killing vector. This gives us a constant quantity. d tau, the derivative with respect to proper time of that is 0. It means that this object in here must be a constant. So k dot u, the fall velocity, is constant. In other words, the fall velocity of the object is constant in the direction of the killing vector. So this condition tells us the fall velocity of a particle is conserved in the direction of the killing vector. K dot u is constant. But we can build from the fall velocity the fall momentum simply by multiplying by the mass. So we can also say that the particle's fall momentum is also conserved in the direction of this killing vector, because we're just multiplying by a constant. So constant times a constant is just another constant. Now these results hold in both flat and curved space-times. And so the next thing I want to do now is, okay, well, how about a swarm of non-interacting particles? So up and above here, in previous slides, we've been looking at a single particle, freely falling particle, not subject to any forces, freely falling in either a flat space-time or a curved space-time, doesn't matter which. Okay, we've been looking for the geodesics. Okay, we've introduced the idea of symmetries and conserved quantities. So how about now, and the point of making this video was, how about a swarm of non-interacting particles freely falling in some space-time? Okay, so freely falling, non-interacting, so they're all, each one of them, each following its own geodesic, and they're all falling together, freely falling. Okay, so each of the particles in a swarm is moving along its own geodesic. We can expect the energy momentum tensor to be conserved along a geodesic in the direction of a Killing vector. And we can represent the energy momentum tensor in any of these forms here. They're all equivalent. Okay. Now, what will help us here is to realize that when we talk about observing or measuring quantities like energy and momentum, we must do so from the orthonormal basis. If we want to make an observation or a measurement of something, then we need to do so in the orthonormal basis. Remember that observer and his or her freely falling observatory in space-time. They were using the corner of they're using the axes of the room, the corner X, Y, and Z axes of the room as their orthonormal basis from which they made their measurements, and the clock is their time vector, time basis. Now, normally we work in general relativity in the coordinate basis, okay, because our manifold is in terms of coordinates and positions and so on, and our basis vectors change from point to point. But if we're going to perform a measurement at a particular point in space-time, then we need to do that against an orthonormal basis. We need to work against a basis that is of unit length and orthogonal, and make all our observations and measurements relative to such a system. Okay, so and if we want to measure things like energy, momentum, and so on, then we need to do so from the orthonormal basis. So we perform calculations in the coordinate basis, where the basis vectors of the inner product, scalar product of the basis vectors, is our metric. But but we observe and measure in the orthonormal basis, where this gives us the flat Minkowski space-time metric. The scalar product of the basis vectors in an orthonormal basis system gives us this relationship here. All right, they're of unit length and orthogonal. And so the scalar product, the inner product, gives us the flat Minkowski space metric. And that's the difference between the coordinate basis here and the orthonormal basis. So the two bases are related to each other in the form E0 hat is 1 on the square root of minus G00 for whatever metric you're in, whatever metric you're using, times the coordinate basis vector E0. Okay, or the other way around. The coordinate basis is this object times that, times the orthonormal basis vector of the same component. The spatial ones follow this pattern here. All right. Now, let's rewrite the energy momentum tensor in the orthonormal basis. So here we are. I'm just going to raise this index. I'm going to lower this index just for ease of convenience, and I need to use the inverse metric to do that. So now I have coordinate bases all in the lower position, all the tangential basis vectors, okay? And I can now transfer this one into this orthonormal basis, and this one is rewritten here as this orthonormal basis. Notice we have these metric terms here. There's no summing over mu mu, it's whatever value this is, these take. So if that's the first spatial component, then this will be 1, 1. Okay. If that's the 0 element, then this will be 0, 0. Now, we need a killing vector such as, well, let's use this one, just for argument's sake. This component here is 1. Now, the inner product of this with our energy momentum tensor is, so we're asking, well, this energy momentum tensor in the direction of this killing vector, let's see, are we going to find a conserved quantity or not? All right, so T dot K, this object here, is the scalar product here. Okay, and now notice here, E alpha hat and E T hat. Okay, here the flat space metric applies. So that'll be the TT term, which will be -1. So we get -1 here. Okay. GTT is the same as for a diagonal metric, 1 over GTT. Okay, if we're working with a diagonal metric, then we have 1 over GTT times that. Okay, and we're left with this object here, E mu hat. Remember, these two basis vectors have been contracted, and we've produced the scalar -1. Okay, and we're left with this object here. This is, as you can see, it only has a single basis vector. It is and so this whole thing is a vector object. we've contracted down using the killing vector. We've contracted this down to a rank 1 tensor, which is a vector, and in this particular case, the momentum density vector. Okay, we'll just call that A. Now, the conservation of a quantity such as a momentum density vector in the direction of a killing vector is expressed by del dot A is 0. Divergence theorem there, if the divergence is 0. And just to remind ourselves how we can use that in Euclidean space, Gauss's law is this object here. The integral of the divergence over all the spatial dimensions is equal to a surface integral over over a space that's one dimension less. All right, surface integral. So in 4D space-time, the equivalent is this. Divergence here, volume element, integrating over 4 space, volume element here, over a surface integral of and an induced metric of 1 dimension less, d3 instead of d4. So with normal vector to surface, with the normal vector to surface of constant time being, now for our surface here to evaluate this, we're looking at a vector there which is normal to the spatial surface, so the time vector is just that. So we're looking at surfaces of constant time, and we're going to compare the whole system of the swarm of particles at one time to a previous time. So we're going to but what we're going to find is that our normal vector, which is normal to the surface of constant time, the swarm passes through a surface of constant time t1 and then at later time t2, but each of those vectors, normal vectors, will be the same because this is constant. Remember, the time component was independent. The metric does not have a time component. And so we can develop a killing vector in that direction, which is what we've done. But we can also use that surface of constant time here, and we find that each of these normal vectors are the same. And so when we perform this analysis later on, we'll see what happens with that. But just before I do that, let's work out this bit here, A mu, N mu. Okay, so we took our momentum density vector, we dotted it with the time basis vector, the orthonormal basis vector. Okay, flat space metric applies here. Okay, so we have this object here minus all this times -1 eta tt, the 0, 0 component is -1, and that gives us this object here. Okay, since kt is 1, we can also write it like that, but this is the time component, the energy density, if you like, is what it is. It's the energy density of the momentum tensor. Okay, evaluate that integral over 3D space, evaluating the surface integral over 3D space, I should say, that's this one here, and we're evaluating at time t2 minus time t1. And when we perform that integration here, okay, what we're left with is the integral of this minus this. Nothing's changed because here, if you look here, t1 is the same as t, tt in here, they cancel. t2 is the same as t, these dotted, so tt over t, they cancel. We're left with this object here, which is 0. Okay, and because we have this mu, the only variable then operating, mu can only be t here because for all others it's 0. So the whole thing goes to 0. The only non-zero part is when mu is equal to t. That's this object here. Okay, that means that is that, and that implies that that is that. So that the divergence is the derivative with respect to time of the time component of the vector A. When we do that, we get this is 0. So the partial derivative of the energy density with respect to time is 0, which means the energy density is constant, all of which indicates that del dot A is 0. So our momentum density vector, which is what we achieved earlier, this A vector, is conserved in the direction of the killing vector that we've used, which is one in the time basis, in the time direction. All of which shows that A equals t dot k, the vector A, which was the rank 2 tensor t, the energy momentum tensor contracted with a killing vector to give us a tensor of rank 1, which is a vector, is a conserved quantity. So the inner product, the energy momentum tensor with a killing vector, produces a second vector quantity that's conserved in the direction of the killing vector. In the coordinate basis, we say that t mu t kt is a conserved quantity in the direction of the Killing vector kt. All right, so there are conserved quantities in the direction of Killing vectors, not just the fall velocity or fall momentum, but even the energy momentum tensor itself produces a conserved quantity. I've almost finished this section on energy momentum tensor. I may just make one more video just looking at a small proof of the conservation of the energy momentum tensor in the direction of a Killing vector. And that may be one small supplementary video, and then I'll be done with this bit. All right, finished.